So have you calculated, finished the calculation? Let's just see the result because I think we try to save some time. So you can substitute the coordinate and also the major h values, and then you can get the equations like this. And after that, you can solve the A, B, and C to get the result. And then you can calculate the hydraulic gradients in the x direction and y directions. The quantity will become like this. So that means x gradient is positive and y gradient will be negative. So that means these directions. X is positive and y is negative, so your direction should be like this, right? Is that okay? Gradients. And then your combined hydraulic gradient will be these quantities. And after that, you can calculate the values for the angles. Okay, so there's the angle C divided by B. And you can be the radius, and after that, you can calculate to be the degree of the quantities. So that means there will be minus 13, this angle like that. So this is the final result for your calculations like that. Is that okay? I don't know if you are the same or not. A little differences could be okay. Yeah, but this is to let you understand. For the old time, if you do not have any software or you do not have any PC or some machines to help you doing some identifications, you go to the institutes. They have 3 points to let you understand how the groundwater flow look like. You can use in this kind of methods to provide your boards or your others to let them understand approximately the gradients like that, and you can have the flow behaviors. And another part is you can see the head here is higher. This is lower. This is lower. So your water flow should be like these directions. Okay. And another method, more quickly. Commonly, right now, we have some of the tools like softwares, like you have the interpolations methods. You put the data in the software. They can help you directly estimate the flow net or the equipotential line, like the water flow contour line. So you can also use in the software to help you solve the contour line. There's another you can very quickly obtain. If you have the contour line perpendicular to the contour line will be the flow line, right? You're easy to identify how the water flows. And the same concept, if you would like to use in the contour line, you can approximately doing the calculations. 57 and 55, so they'll be higher. So 57 could be around this here. 56, 55. Okay, you can approximately identify the line. Okay, the point. 57, 56, 58, and the same. These directions you can approximately calculate. This is 52, 57. So 57 could be here. This is higher, right? And then decline like that. And after that, you can connect 57, 56, and 55, right? You can do the connections like this. So this is approximately the equipotential line. And perpendicular to the equipotential line will be your flow line, your stream line. Okay. So this is the directions. Approximately, but maybe the angle is not correct, but at least you will be able to provide approximately how the water flow. Okay, so this is more quick methods. And previous one will be more precisely the quantities you can calculate. And this one is approximately how the flow look like. Okay. And after you have the hydraulic gradients, you can use that to calculate the water velocity. So that means you should know the hydraulic conductivity to do the estimations. And we showed this before. If you have the clean sand, the quantity are commonly used in meter per second. That could be 10 to minus 2 to 10 to minus around 6. Okay, these quantities, or 2 to 5, or sometimes they are like this. So there's a clean sand. That means they are easy for the water to flow. And also some of the concept, we commonly say what is the good aquifer system and what's the permeable or what is impermeables. So there will be several reference for you. Relative permeabilities, that means we define previous, that means they are permeables, semi-permeable and impermeables. But there's for general concept, not totally correct. And if we want to define the aquifers, the good, poor, or non-aquifers, so you can see that commonly we use in the meter per second. So your K values smaller than 10 to minus 8, they become, we call the impermeable, or they become non-aquifers. They become aquicrude, aquefuge, or aquitar, like that. And poor aquifers could be around 10 to minus 2 to 10 to minus 6. And good aquifers, oh no, should be this one, okay. So good aquifers commonly is higher than 10 to minus 4. So they are relative good aquifers. They approach to the sand, gravels, yeah, like that. Fine sand, commonly they could be a little pool, or silt, they will be small quantities. Okay, so there's some of the reference for you if you would like to do the comparisons. And there will be clay. Clay total porosity is very large, but I mentioned that effective porosities, they are very, very small, okay? And the hydroconductivity is much more small, okay? So there's general concept. Porosity higher, but they are not easy to flow. But since they have high porosity, they are easy to be compressed. Okay, they have a lot of empty space, so they can be compressed. And they are not easy to flow because hydroconductivity describing how the water flowed. Okay, and effective porosity also describing how the water flow in the system. And following is the methods we commonly use to estimate hydraulic conductivities. In the previous, we used in Darcy's experiment to do the estimations. And Darcy's experiment is for the laboratory experiment. But there will be several methods we can use to quantify the K values. It includes the in situ field measurement and laboratory methods, and the other could be the empirical approach. Okay, sometimes we separate to these three methods. And for the laboratory methods, we use in the constant head or falling head. Constant head is the Darcy's experiment. We fix the inflow and outflow head, right? That's the Darcy experiment. And we propose another is the falling head methods because I mentioned that in the Darcy experiment, we need to let the system reach steady state. But right now, if your porous media is very difficult to float, like using a fine sand or using a silt material, you want to estimate how large are the K values. You need to wait the system to reach the steady state, maybe take 1 week, or maybe much more, 1 month, to let the system reach its steady state. It wastes time. So researchers try to propose another method called the falling head methods. You don't need to wait. You just measure first time and second time and see how large differences the head changes. You can directly use that to estimate the K values. So that means we use in the falling head, the head will change with time. Later we will have the methods to let you understand that. And for the in situ test, we commonly use in the pumping test. Pumping test. Pumping test is the traditional method we use to understand how large are the quantities. And another could be the slug test. And there will be differences between pumping test and slug test. Later we'll introduce that. Okay, so this is commonly used. And for the empirical methods, we're using several parameters to estimate approximately how large are the K values. That could be small k or capital K. Small k means intrusive permeability. Capital K means hydraulic conductivity. We're using a pore size distribution, grain size distribution, or some soil textures, or the soil mapping unit, several parameters to estimate that. That's an empirical approach. Okay, and for the in situ test, this is more traditional or more important to obtain the K values. We're using a pumping test, and there will be some characteristic or some importances. Pumping test and slug test will be also very similar for the concept, but they have finer differences. Like I mentioned, we're using Darcy's experiment or using constant head or falling head methods, depend on some of the limitations. So we propose a new concept. Pumping test, it takes much longer time. For the formal, they can take 1 week to finish all the pumping test step. So it takes much more time, and you need to pump a lot of waters. So researchers try to propose another method called slug test, and they consume less water pumpings and time. You can save more time. So we use in the slug test, but they still have some limitation and applications field. For pumping test is for a relative larger scale and for high transmissivity field. What's the meaning for a larger scale? Because when we're doing a pumping test in one site, you pump 1 week. That means your inferences area could be very large because you pump a lot of the waters, you pump amount of the waters out. There could be tons per day, okay? So you pump a lot of water. So that means you disturbances the areas quite large. And they also represent that your K values or T values could be the average for that area. Okay, so we call this a larger scale concept. And for the slug test, we disturbances the water very slightly. For example, we inject amount of the water that could be 10 liters, or we take waters maybe 2 liters. So we disturbances the aquifer system slightly. So that means their disturbance areas could be very small, could be meters, 2 meters, 5 meters. Okay, so the scale would be small. That also means that your T values or your K values only represent that small area. Okay, and K value, the pumping test can have larger inferences. So their representative K or T will be larger. This is also very important. When you gather the data from slug test or pumping test, you should have the concept that slug test only represent a very tiny area, and pumping test can represent a site area. Okay. For example, in the contamination site, commonly we use in slug test because they are not allowed you to pump a lot of the waters. So we can only small disturbances in the system. And your T values or your K values only represent a small area. And you cannot assume that K values is correct. You need to fix that for the in situ experiment or for the numerical models. It's not correct because it only represents a small area. For example, your grid size could be 10 meters cross 10 meters. So that means your T value, your K value for that point only represent that grid. Outside it will be totally different, okay? But if you're using pumping test, that could be, for example, 50 meters. That means if you're using 10 multiplied 10, so they can inference your grid size more largely. Several grids can be combined. So remember that when you input your T values, K values in your model, they are the initial guess. They are not the real. So we need to adjustment your parameters to fit your observations. And then we call the inverse, or we say the calibration step to let your system match the reality. And all your initial setting is just an initial guess. It cannot be trusted. Okay, remember that they have the scale inferences. And another is that for high transmissivity field and for low transmissivity field. For example, when we're doing the pumping set, we pump a huge amount of the waters, relatively huge. Okay, if you doing a pumping test in a fine grain material like in Jianan plant. Jianan plant commonly they are very fine grain material, and you using a very strong pump in that area. What things can happen? Your well have the waters there, but after you pump, the water decline very quickly because the water is not easy to flow in to recharge to the wells. So you cannot pump too fast. You need to pump slowly. Okay. So that also means that if you have the high transmissivity field, you can use in the pumping test because it collect more waters. But if you have the low transmissivity field, it is not suitable to use in a pumping test. Or you should use in a small pumping system. The pumping rate should be smaller, okay? And the same concept, if you using the slug test in a gravel system, like the proximal fan area, using the slug test, you inject, for example, 2 liters of the waters in the system, in the wells. What happens? Your original water level here, you inject 2 liters, because they are easy to transmit waters. So the waters increase immediately, but also decrease, go back to the original levels immediately, or in a very short period of time, could be several seconds. But when we're doing this kind of test, we put the pedometers in the wells to do the measurement for the levels changes. We're using the level increase, decline, or decrease, go back, recovers. We're using the curve to do the fittings, and we can estimate the K value or T values. But if the levels go up and go down quickly, you cannot measure the differences. You cannot measure the recover period. You will not be able to do the test. Okay, so slug test, we disturbances very slightly. So your material or your aquifer system should not have high transmissivity, because you will transmit the water very quickly or too quickly. You will not be able to detect or to observe the decline or recovery behavior. So they have the limitations for this. Commonly, pumping tests they have larger inferences. They have the larger scale result, and they commonly using for the high transmissivity field, because you need to pump relative large amount of waters. And slug tests commonly for the relative small scale, because they only disturbances the aquifer system slightly. And they commonly using for the low transmissivity field, because we need to see the inferences, uplift, decline, the curve, or the decline, recover the curve. We're using the curve to do the fittings. So we need to have the observations. So it do not be able to using for the larger pore spaces like gravel. Okay, so that's the concept. And Professor Chunfani, they will help us doing a pumping test, maybe in Taikos or in other place. We can directly take a look at the pumping test system. And I show videos for you what is a slug test, and this is one of the slug tests. Slug tests could be several. Okay, so in the final, they take up the parameters because they will do some measurements. The concept will be that we have the wells, we have the water level here. So this one, they using the pressures, not to inject the water or take out the waters. So there'll be several kinds of slug tests. So they try to inject the airs inside. So they induce the increase of the water pressures. So the increased water pressures will induce the decline of the levels. Right? So after they doing that, for example, the outside could be water levels in the aquifer, and the wells, it declines a little bit. So after you inject the airs and then you release, so you can hear that they have the release the pressures. So after the pressures go back to the atmospheric pressures, they will come back, or they will gradually come back. So the waters flow in or flow out. We can measure the parameters. So we can understand that how fast the water flow from the aquifer to the well. We measure the differences. So we decline the head and let the head recover. Okay, so your measurement will be the head and time. Your measurement will be decline and then recover to the original levels. Your head will be like this. Okay, like you take waters out. So when you take water out, they decline the head, so the water will flow into the wells. And what we measure, the K values or T values, is how fast the water flowed from the aquifer to the well, or from the well to the aquifers. Okay, so we measure the velocity, so we can use this curve to estimate how fast the water flowed. Okay, so this is the concept for this slug test. And for the pumping test, this is in our campus, we have the several devices like the Professor Ni's lab provide. We have the computers here. We have the control for the pumping rate. And all of that is connected to the pumping system. And we put, in the beginning, we commonly doing the measurement first. We using the pedometer, man-made, or the human measures. Okay, we try to detect how depth the waters. This is the first step. And after that, we can use that to set up the pedometers. Because pedometers, they will measure the quantity, how depth the waters they might have. They have several settings. Yeah, this is very detailed, but I want to emphasize that. So after doing the measurements, we will see the water level decline when you do the pumping test. And when you cease the pumping, they will go back. And pumping again, and cease the pumping, they'll go back. Okay, so commonly the curve will like this kind of the system when you're doing some pumping test. And this kind of pedometer, commonly they have the pressure and also temperatures. So the other could be the temperatures variations like that. Okay, so this is the pumping and observation at the same well. But commonly we're doing the pumping at the one well and observation at the different wells. Or all of that will have the observation system for this. Yeah, this is for measurements. This one is the sensors. When you touch the waters, you will have the sound. Okay, so you can use that to measure. They have the rule here, so you can easily understand how depth the waters. And we commonly measure for the well top. Well top, we can define the elevations, absolute elevations compared to the mean sea levels. And we can use in that values and also the depths, we can identify how the water levels it might have. And remember that water level is the elevations, absolute values compared to the mean sea level. Okay, so we need to use that to identify which one is higher, which one is lower. We cannot use in the depth, because depth, they have the elevation differences. So you can hear that, okay. Touch the waters, they will have the sound. And you can know they touch the water. And you try to check which one just touch the waters. And then you can mark the point with the well top and take out. So you can measure the well top from the well top to to the waters. So touch this point, so you can measure this one. And commonly this point, we will have the elevation, well top elevation, like maybe 23 meters. And if you measure this one is 2.5, you can minus, and then got your water level will be 23 minus 2.5. There'll be 21.5. So that's the water level elevations. Okay. In the groundwater levels, we always using elevations because they compare to the mean sea levels. We will be able to know which one is higher, which one is lower. Okay. It's the kind of the potential. So remember that elevations is elevation, not the depth. And this is the pump we put in the waters. Commonly you might see the pump on the surface. This kind of pump, they pump the airs out. So they decrease the airs in the tube and then suck the waters to the surface. But when your water depth is quite deep, you cannot use this kind of suction system to take the waters. So we put the pump in the waters. We put the pump inside and then push the waters out. And this one is we call another pump, 沉水马达. Okay, it put in the waters. And this one relatively expensive. So they need to have the electric pipe, electric tube to connect to the surface. So in the pumping, when you would like to do the pumping test, you also need to have the power generations in situ. Or commonly they do not have the power, so you need to try to solve the problem. And the pump, commonly you can shift the frequency. If you shift the frequency, the pumping rate will be different. So we can use that to control the pumping rate. For example, in the following, we'll introduce the pumping test. There will be, we call a step test, step pumping test. You need to test which pumping rate is more suitable. And if your pump, if only one pumping rate, it will be difficult. You need to prepare a lot of pump to do the test. So commonly we prepare one pump and we change the electric power to control the pumping frequency. So we can control the pumping rate. And then after we test several steps, we can know which pumping rate is more suitable. And we use that to do the continuous pumping test. Yeah, that part we will introduce in the following class. So this is you can see there'll be the tube here that connect to your pump. So in the pump, they will have the cables, electric cable to supply the power. And another, they need to connect to the tube to pump the waters out, okay? So there'll be several devices you need to put it in the wells. If you put another parameters in the well, so you will have several lines, cable lines in the well. So commonly, the pumping well will be relatively larger size radiums. That could be 4 inches. And observation well could be around 2 inches. So if you would like to use in a pumping test in a small scale, that will be difficult. Your pumping device cannot put it inside. Okay. So commonly, pumping well will have larger scale. 4 inches is better. Okay, he mentions that the depth to the waters is around 5 meters. I mentioned that this one we call, I don't know how to say in English, 扬层. That means the distance from the surface to the water surface to the ground surface. Because you need to decide your pumpage if they are powerful enough or not. If your water is very deep, that means you need to have more power pumping machines, and then you can pump the sufficient waters out. So we will consider this one we call 扬层. Yeah, this is very important to decide your pumping. So you need to know how depth the waters, and then you need to put your machine lower than the average elevations. Because when you're doing the pumping, the water level will decline. For example, if your pump put here, and it will become like this, your water level will decline, and then this one will burn because it becomes dry. So your pump need to put much lower. After you're doing the pumping step, they have the decline of the head, but they still lower, your pump still lower than your head. That's the reason why we need to find a suitable pumping rate. If you do not test your pumping rate suitably, your pump could pump too slowly or too fast. You will induce some damage. And the suitable pumping rate in the report or in Taiwan, we call self-yield. But this one is totally wrong. I'm not sure in English if they call self-yield or not, but in Chinese they call 安全储水量. This self-yield is totally not the water management self-yield. Self-yield is totally different. This self-yield is to confirm your pumping rate will not over the supply of the water from the wells. So we can do in the pumping test without problems. So this one is to protect your pumping machine, not related to your management. When you consider the groundwater management issues, we will have the self-yield. But this self-yield is this area, how much the water can supply for your water usage. And this self-yield is not this self-yield for the pumping test. Okay, totally different. But right now in Taiwan, a lot of the project, they're using this quantity to say, yeah, this is the water they can provide. We should use in this quantity if my pumping rate lower than this, without any problems for the water supplied. Totally not, okay? Like in the hot spring area, the company say, oh, the self-yield is quite large, but I just pump in half, so they will not have the influences for the environment or for the water resources. This totally not. This one is only for the pumping test, not for the water management, okay? Very important concept. And after we doing the pumping test, the water be pumped out. So we try to drainage the water to some of the canal. And remember that this water needs to away from your pumping wells. Because if you just put nearby, they will infiltrate to the groundwater system. And when they infiltrate, it will influence your pumping result. Okay, so commonly we need to drainage the water to the other areas to let the water go out. And this one is the measurements, how fast the water flowed. Traditionally, we might collect using bottles to collect the water and count how many seconds or minutes, and then we can have the flow rate. Traditionally like that, but right now, if we have the flow meters, we can set up a flow meters. It can directly tell us how fast the water flowed. Okay, yeah, something like that. Okay. So that's the pumping test. Is there any question for that part? We'll go to the institutes to demonstrate maybe still the Qiping. Dr. Lin will demonstrate or others. Yeah, Person's lab will help us demonstrate that because I do not have the device for the pumping test, but they have plenty of that, okay? And following will be the laboratory methods. We have the constant head method and falling head methods, okay? So right now is the test to confirm if you understand the Darcy experiment. Okay, so this is the constant head methods. This is the falling head methods. Okay, constant head method. The first question will be how the water flowed from here to here or from here to here. The flow direction is upward or downward. Give you 10 seconds. Think about the flow is downward or upward. Do you decide? Okay, we vote. How many of you think they are upward? How many of you think they are downward? flow direction downward. Several do not vote. So what's your decision? Okay. The same I mentioned when we have the Darcy experiment. Find your target first, right? This is our target. The soil body is here. And this is sealed, so they do not have the flow. So they need to float from this surface and this surface in or out. And then let's check. This is the flow in. We need to know the total head here, right? And we need to know the total head here. So what is the total head here? If we set up the datum to be here, okay? That means we have the elevation head and pressure head is where? Pressure head. You can see the tube. So your pressure head is here, right? This, do they mark? Okay, they do not mark. Yeah, but this is the total head. So they have the elevation head and pressure head. And then this point, this surface, we have elevation head, pressure head. So the total head is here, right? So that means this surface, we have the total head. This surface, we have total head. So it means the head here is higher, this head is lower. So the flow from here to here, okay? Not due to the gravity. If you think about gravity, oh, there is higher, this is lower, they flow downward. No, it's not. Okay, they flow upward. So very important, very important. And then you can see that. So at this surface, they have the total head is H1, and this surface they have the total head is H2. Not here, okay, because your head is here. So this is your total head or hydraulic head. This is not here. You need to combine them together. Yeah, or you can use in this one to be the 0 is also okay. Elevation is 0 is also okay. But if you use the datum to be here, so your total head is here. And all of that could be okay because your head differences will be the same. Your head differences is from here to here. Okay, so this is your head differences. And then you can calculate your hydraulic gradients. Distance flow from here to here, the traveling distance is L, right? L, and your head differences will DH. So you have the DH divided by your L, that will be the hydraulic gradient. And we have keep the constant because you have the flow in, continuous flow in, and they will flow out. If they over the levels, they flow out. So you keep the constant. And the same, if they flow out, they still keep the constants. And after the system reaches the steady state, you can calculate the flux, the total flux with time, and then you can use in the Darcy's experiment or Darcy's law to calculate your K values. Q equal to K, I is this part, and A, right? If you shift the part, they multiply here, L divided by, become the lower part. So using a Q equal to KIA, you can calculate your K values. So this is the constant head method using Darcy's experiment. Although they look like a difference with the previous, but the same concept, okay? And falling head methods, the setting could be very similar. The only differences will be this part, okay? In the beginnings, we set up the initial head to be here. And you open a valve to control the flow. They start flow and then stop. So the initial here, and after a period of time, it declines to here. So they will have the head differences, okay? So the initial H0 and the final will be HL, okay, they're using HL. So we'll have the head differences. And we using the volumes, for example, if you have a cross-section for the tube, and you know the distance and multiply the cross-section, you know how much the waters disappear, right? And the disappear means they need to flow into the system. And it should equal to the flow out quantities. Your flow in need to equal to the flow out. So you can estimate also the volumes, and then you can use in the balance concept. Flow in equal to flow out balance, and you can derive the equations. And after you derive the equation, you can also have the correlation with the K values. Okay, because we have the time, we measure how fast the time flow in and how much the time flow out. So we can have the time term here, T1 minus T0 initially, and then the final time. For example, maybe you just count 5 seconds or 10 seconds or several minutes. Depend on the material. If you're using a clay, that could take hours. But if you're using a fine grain material like fine sand, that could be several seconds. They can decline. Okay. So I mentioned that if this is gravels, that could be very quick because you start and stop very quickly because they will decline very fast. So commonly when it is fine grain material, we are able to use this. And the same concept, if they are fine grain material you use in this system, you need to let the system reach the steady state. It takes week or months. So it becomes not efficient. So we use in the falling head test. So commonly falling head is the material could be finers. Okay? So they have some limitations for this. And following will be some videos. This is the same. I skipped. If you, I will upload the slides. You can take a look. They have the derivative for the equations. You can take a look by yourself.
This is a tutorial for the Hydraulic Conductivity Lab, the Geotechnical Engineering course, Civ E 3208. The purpose of this lab is to determine the hydraulic conductivity of a soil sample. Hydraulic conductivity is a property of the soil which determines the rate water will pass through it. It is important to be able to know how to measure hydraulic conductivity, as it is a factor in applications like dam and landfill design. There are two types of hydraulic conductivity tests: a constant head test for coarse-grained soil like sand and gravel, and the falling head test for fine-grained soil like silt and clay.
The time is not sufficient, but we try to finish
for the
that.
constant head test. Connected to this reservoir are 3 lines. An intake, which is connected to a tap and will keep filling our reservoir. A discharge line, which will take extra water out of the reservoir and keep the water level constant. And a line with a valve, which connects to the test cylinder.
The system could be different from the previous what we see.
About 1 kilogram of coarse
So it depends on the settings. You can also have your own design.
Record the mass of the container plus the soil in a table. Place a screen at the bottom of the cylinder. This prevents the soil from being carried out. Fill the cylinder with the soil sample. Split the soil into about 3 layers, and compact each layer with a hammer, like this. If your objective is to determine the conductivity at a specific density, measure the mass required given the volume of the cylinder, and compact the sample enough so that it completely fills the cylinder. The top surface of the soil in the cylinder should be level with a small space for the screen and end cap. Place the screen on top of the soil as well as a separator. Next, place the cap on top of the cylinder and secure it with 3 screws like this. Record the mass of the container plus the remaining soil. Connect the intake line from the reservoir to the barb at the top of the test cylinder. And connect the tubes for the 2 manometers to the 2 outlets on the side. These are for measuring pore water pressure at specific points. Before filling the reservoir, close the valve on the intake of the test cylinder. Turn on the tap and let the reservoir fill up. Once the level of water in the reservoir reaches a certain level, it will start to discharge into the sink. When this happens, the level of water is constant, and we can begin the test. Now open the valve to let water into the sample. Before we start measuring flow rate, we need to let water run through the sample. This is to remove any trapped air. Let the water run through the system for a few minutes. Here we can see the pore water pressure being recorded on the 2 manometers. Now we can start measuring water flow rate. Take a beaker like this one, then measure and record its mass in the table. We'll be using this stopwatch to record the time. Simultaneously start the stopwatch and begin filling the beaker with the discharge from the test cylinder. Here we are aiming to collect about 300 milliliters of water. Simultaneously stop the stopwatch and remove the discharge. Now record the mass of the water plus the beaker, as well as the time it took to fill in seconds. Empty the water and zero the stopwatch to reset. Repeat this test 2 more times, each time aiming for a different amount of water. Before we finish, we need to calculate the head applied to the sample. To do this, measure the total head at each manometer from the base of the cylinder. Here, the head height of the top manometer is 49.8 centimeters and 11.3 centimeters for the bottom manometer. Finally, record the difference in height between the outlets to the 2 manometers. You can draw a line around the outside to help you do this. In our case, this was 16 centimeters. We can now clean up the apparatus and proceed to the calculations. Calculate the cross-sectional area of the cylinder. To do this, take calipers and measure the diameter. From this we get the cross-sectional area, as the section is circular. The coefficient of permeability for the constant head test is given by this equation, where Q is the volume of water collected, L is the sample height, A is the cross-sectional area of the soil specimen, H is the total constant head, which is the difference in head between the 2 manometers, and T is the duration of water collection. Calculate K for each of your 3 tests. And finally, calculate the average of these 3 to get the final value for conductivity.
Okay, so there's the constant head test.
First we need to put together the test cylinder. Unlike with the constant head test, which uses a screen, the falling head test uses a porous stone. Place the porous stone on the base like this. Now place the tube which acts as the cylinder's walls over top of it. Then thread the end cap with a hole in it onto the 3 protruding screws. Secure it with 3 nuts. This is to create a tight seal. Now obtain a soil sample. Similarly to the constant head test, measure out approximately 1 kilogram of soil into a container and record the mass of the container plus soil. Place the soil in the test cylinder like this, again compacting the soil into about 3 layers. In this experiment we are using a fine-grained sand, although this test is best done with silts or clays. Level the soil at the top of the cylinder. Place the second porous stone on top of it, and then thread the end cap on, securing it like this.
The setting is similar.
Finally, record the mass of the soil container plus the unused soil. The cylinder for the falling head test consists of just one line connected to the test cylinder. Connect the line to the cylinder. Before we can start the test, we must saturate the soil with water. There are 3 valves in the system. Make sure they are all open. Start adding water to the top of the stand pipe. A larger funnel can help you do this more easily. As you can see here, water will start moving into the test cylinder and saturating the sample. When water starts coming out of the nozzle at the bottom, as you can see here, we can proceed. If there are bubbles in the pipe, gradually add more water to the system so that the air can be flushed out. Close the valve at the top of the test cylinder so that the water level in the pipe remains constant. If there is water left in the funnel, open and close the valve so that the level of water in the pipe falls to a measurable level. For the first test, use a stopwatch to record the time it takes for the water to drop a certain distance. Start the stopwatch and open the valve simultaneously. Wait for the water level in the pipe to drop a given distance. Close the valve and stop the stopwatch simultaneously when the new level is reached. Record both levels of water, as well as the time in seconds it took for the water level to drop. If the water level is too low, add more. Repeat this test 2 more times for 3 readings in all. This is the equation for the coefficient of permeability when performing the falling head test. Lowercase a is the cross-sectional area of the stand pipe. The internal diameter is given to us as 6.6 millimeters. From this, we get the area. L is the length of the soil column. In our case, the length of the column is 16 centimeters. Uppercase A is the cross-sectional area of the soil column. In our case, the diameter of the cylinder is 6.3 centimeters. Therefore, the cross-sectional area is 31.2 square centimeters. T is the length of time taken for the head to drop. H0 and H1 are the total head before and after each test, respectively. Calculate K for each test. Finding the average value of K between all three of our tests gives us the hydraulic conductivity. This concludes the falling head test in the hydraulic conductivity lab.
Okay, so this is approximately to let you understand what is the constant head and falling head test. And based on this kind of setting and measurements, you can input it to the equations to obtain the K values. Okay. Yeah, there will be some tinier detail I will not explain too much. I will stop here first, and next week we will have another new content. And I will repeat some of the contents again to let you more familiar with what we talked today. Okay. Any questions about today's talk? If no, we stop here. Okay. Thank you very much, and remember to provide me your team title and team members. Okay.